In today's video, we're going to be talking about states of matter. And after watching this video, you should be able to define the three most common states of matter, be able to understand and interpret heating curves, and then be able to use the heat of fusion and heat of vaporization formulas. And I will be creating a separate video on how to work those problems. So if you're struggling with any homework problems that involve heat of fusion or heat of vaporization, check that video out. And as always, you can refer to book pages 323 through 325 if you're looking for some extra reading or help on this subject. Okay, so the three most common states of matter would be solids, liquids, and gases. Water is probably the best example for using this because you can find water on Earth in all three states. You can find it in snow as a solid, liquid water from like the drinking fountain as a liquid, and then in the air you certainly can feel it when there is a high humidity. It feels very sticky, and that's water as a vapor or a gas. Just kind of keep in mind that solids, liquids, and gases all have kinetic energy, and that basically is saying that everything has, it's made of particles, and those particles are moving, and kinetic energy is movement. And so these molecules or particles are either vibrating very quickly in a solid, or they're actually free flowing in a liquid or a gas. They also have potential energy, and we'll talk about how they have potential energy. Basically, it's this attraction between the molecules that can be seen in these heating curves. The only time that these substances would not have kinetic energy would be if absolute zero had been reached and basically all motion has stopped in the particles. Now, as I stated in a previous video, we've never actually reached absolute zero yet. So does it actually exist in the universe? I would probably be willing to bet yes, it does somewhere, but we haven't found it yet. So this is a heating curve, and this is a heating curve for water. So basically, if you take, say, a hunk of ice and you stick it in like a beaker or something like that, and you measure the temperature, you'd be down here at negative 20 degrees Celsius. And you start to heat that hunk of ice up, and it gets warmer and warmer and warmer until it hits this point, 0 degrees Celsius. And 0 degrees Celsius is the temperature at which solid ice starts to melt and turn into a liquid. And you'll notice what's kind of interesting is for a period of time, this ice flatlines. It stays on this flat plane here. Why is that? Well, basically, until all of the ice has melted into a liquid, the temperature does not change. And so what's actually happening is the heat is going into basically breaking down, not breaking down, but making the particles of water separate far enough so that it can become a liquid. And so during this phase change here, it's not so much that you're gaining kinetic energy because the particles aren't moving faster per se, but you're actually gaining potential energy as you heat it up. Or on the flip side, if you're cooling it down, you're changing a liquid into a solid, you're losing potential energy. And once all that solid ice has melted and it's become a liquid, then you notice the liquid starts to increase in temperature, starts to go up again. And again, you're gaining there primarily kinetic energy because the molecules are moving faster and faster and faster until you hit this number 100 degrees Celsius. And that's basically when liquid water changes into a gas, and that starts to vaporize. And you notice again, it flatlines during that phase change. And really what you're gaining there is potential energy, not so much kinetic, but more potential energy during this phase. And then you can heat the gas up higher and higher and higher to a point that we don't really care about. Now this is just for water. There will be different numbers for different substances. So I mean, steel melts at a different temperature than say water does. So that's why water is such a good example, because you can see solid, liquids, and we know gases are here all on Earth pretty easily. All right, so the first thing I want to talk about is this thing called heat of fusion. And basically heat of fusion is the amount of energy needed to melt a unit of mass of a substance. And that sounds real fancy, but basically what it boils down to is how much energy does it take to, say, melt a hunk of ice? Or how much energy would it say to take to melt a hunk of iron or steel or copper or whatever the case may be? So how much energy is needed to be put into this object to either melt it, or on the flip side, how much energy must be taken out of the object to make it change from a liquid to a solid? Okay, so heat diffusion can be used to change from a solid to a liquid or from a liquid to a solid. And your formula is right down here. Q equals M, which is mass, times the change in the heat of fusion, which is just a number I will be giving you for whatever object you're using. So water has a different heat of fusion than, say, steel does or copper or that type of thing. And on page 320 or 24 of your book, it has the heat of fusion, and the next thing we're talking about is heat of vaporization of common substances. So again, it's not something you need to memorize. It's a number that would be given to you. The next thing we want to talk about is something called heat of vaporization. The heat of vaporization is basically the amount of energy needed to vaporize a unit of mass of a substance. So this is changing, say, we'll keep with our example, water here, from a liquid state to a gas. How much energy would it take to vaporize 50 milliliters of water? Or how much energy would it take to vaporize, say, 50 milliliters of rubbing alcohol? Okay, and again, each substance has a different vaporization number, and that's something you wouldn't need to memorize. It's something I would give to you. The other thing to keep in mind is that here's the formula for the vaporization of any substance. It looks very similar to the heat of fusion. This Q here can be positive or negative. If it's positive, that basically means that it is gaining heat or gaining energy. And if it's negative, that means it is losing heat or losing energy. So basically, if you are taking water and you're going to change it to a gas, you got to add heat to it, right? I mean, that just kind of makes sense. If you want to vaporize water, you have to add heat, so it's going to be a positive Q. But let's say you're going to condense water, so you're going to take the water that's floating around in the air, well, it's actually a vapor, a gas that's floating around in the air, and you're going to condense it into a liquid. You're going to have a negative Q. It's going to lose heat. And again, on page 324, it has the heat of fusion and vaporization of common substances. Water's in there, I believe steel's in there, copper's in there, stuff like that, may be problems that deal with this. So that would be about it on this video. Again, if you need help with using these equations, I'm making another video, and you can take a look at that for some help on it. We will see you guys in the next video.